Welcome to Beat Physics. In this video, we're going to be checking out some ideas and strategies to do better on the free response section for the AP Physics 1 exam. Now, the first idea you definitely want to implement is this. Most people will say that you need to rank your questions from easiest to hardest. Now, ranking them 1 through 5 is going to take a lot of mental energy and time as well. So what I would do is I would just label them as E, M, and H for easy, medium, and hard. So I'd spend a little bit of time scanning these questions, get a feel for them, and label them as E, M, and H, and then start with your easy questions, and then work your way to the medium, and then the hard questions, and then that way you're going to get the most amount of points possible. Secondly, each one of these questions is conveniently labeled with the suggested time. So for example, if it says suggested time of 13 minutes and you have spent a sufficient amount of time working on these questions and you feel like you've been pretty thorough and it's only been 10 minutes, you don't need to fill up the extra 3 minutes by staring at that question and double checking it. What I'd do is I would save those extra 3 minutes, and then once you get to the medium and hard questions, then you're gonna have a few extra minutes to work on those questions that are a little bit more time consuming or a little bit more difficult. Next, as you're working on these problems, you want to be very familiar with your formulas. So a lot of people look at formulas like they're number crunching machines, and that's not true. In fact, for the AP Physics 1 exam, you're going to predominantly use the formulas as ways to see all the variables that are connected and how they're connected for a particular idea. So once you're working on a problem and you associate it with a certain idea, what I would do is I would write down the formulas associated with it, and you may or may not use all of them, but chances are they're going to be pretty helpful and maybe earn you a point a little bit later. And if it's something that you're not using, feel free to X that out if you don't want the graders to see the formula that you wrote down that you didn't utilize. But I would definitely write those down, see how the variables are connected, and it'll definitely help you through the process. And then lastly, you want to make sure you write a lot of stuff down. What I mean by that is do a lot of labeling, label your variables, label vectors, do diagrams, and make sure you write down everything that's crossing your mind so that you can visually see everything. And also, as I said before, writing more down will show the people who are scoring your test what you're thinking and possibly score you some points that way. Lastly, because you've worked on a lot of physics problems, if you work on something like a Newton's second law question or a conservation of energy question, you're not necessarily thinking conservation of energy or conservation of momentum or Newton's second law all the time. But once you cross one of those problems where it has a major concept, I would write that down. So recognizing that it's related to one of those big ideas will probably score you a point in a couple different areas of the test. So although you are kind of breezing through some of these ideas as you're working out tons of problems throughout the unit, when you're working on the actual AP test, what I would do is I would label those big ideas and then proceed to the details from there. So we're going to be taking a look at 3 free response samples, 1 qualitative quantitative translation, 1 short answer, and 1 experimental design. As I work through these aren't really for concept development, but more so you can see the strategies and mindset of how I'm going through each of these questions so that you'll hopefully implement some of these ideas and then do the best as you possibly can on the AP Physics 1 exam. So without further ado, let's get into it. The first question we're going to take a look at is number 1 on the 2023 free response section. This is a short answer question and it's 7 points with a suggested time of 13 minutes. Now, I've already looked through all of my questions and labeled which ones were easy, medium, and hard. And I started off with the easiest one and moved my way on from there. And I'm keeping in mind that although I might know some parts, there are other parts that I may not know. So if I don't know part B, I might possibly know part C. So what I'm going to do is take a look at 3 of these questions. And like I said, I'm going to start off with the number 1 short answer one. It says a cart on a horizontal surface is attached to a spring. The other end of the spring is attached to the wall. The cart is initially held at rest. So I'm going to go ahead and write V equals 0 right over here. And when the cart is released, the system consisting of the cart and spring oscillates between positions positive L and negative L. Figure 2 shows the kinetic energy of the cart spring system as a function of the system's potential energy. Frictional forces are negligible. On the graph of kinetic energy versus potential energy shown in figure 2, the values for the x-intercept and y-intercept are the same. Briefly explain why this is true using physics principles. So first of all, I'm thinking of the conservation of energy, and it has maximum kinetic energy. That would actually be right over here at the equilibrium position because the spring isn't stretched or compressed, so it has its maximum speed at that point. And then here's where there's some maximum stretch or compression. So I remember that the initial velocity was 0. So there is no kinetic energy at the very beginning. So it means there's all elastic potential energy that eventually gets changed all into kinetic energy and then back from kinetic to potential again. So I just want to make sure that I explain clearly what I'm thinking using main ideas like conservation of energy, and then talk about how they're transferred. All right, so without using too much time and getting way too wordy, I mentioned the conservation of energy, and all of the kinetic energy gets transferred into elastic potential energy because the friction is negligible. Actually, I'm going to change transferred into converted. That seems a little bit more clear. And I'm just going to X it out because I'm going to save myself as much time as possible and X that out instead of erasing it, which is actually a strategy that could be implemented throughout the test. All right, so moving on to the next part. So when the cart is at positive L and momentarily at rest, so it's still at rest at that specific position, a block is dropped onto the cart as shown in figure 3. The block sticks to the cart and the block cart spring system continues to oscillate between negative L and positive L. The masses of the cart and the block are m naught and 3m naught respectively. The frequency of oscillation before the block is dropped onto the cart is F1. The frequency of the oscillation after the block is dropped onto the cart is F2. Calculate the numerical value of the ratio F2 and F1. Okay, so what I'm thinking of immediately is what kind of formulas do I have that I could use. So I'm going to take a look at my formula sheet and make sure I'm clear on all the things that I could use. And the things that I'd be definitely thinking about is how period is equal to the inverse of frequency. And I'm also thinking about the period of a spring, which is 2 pi square root of m over k. All right, so I want to make sure I write those things out just to have that visual right in front of me as I'm looking at the problem. And now I want to develop a ratio where the mass was originally m naught, and then adding 3m to it, it becomes 4m naught. Okay, so we have 4 times the mass. So I'm thinking that this is the original, the period for just the single m is 2 pi square root of just 1m over k. And then for my second one, the period for 4 times the mass is going to be the same exact thing, 2 pi square root of 4m over k. So because everything is all the same with the exception of the 4 within the square root, what's going to happen is you can bring the 2 out front, and then everything is multiplied by 2. So it's going to be the same exact period, except double the time. So if I'm comparing the periods, then I'm going to say period 2 is equal to 2 times period 1. Period 1. Okay, but they want a ratio though. So it says F2 up top. So I have 2 times period 1 over the regular period of 1. So my ratio is 2, but they want the ratio of the frequencies. So I know the frequency is the inverse of the period. So what I want to actually do is invert this, which basically is going to flip this, and then it's going to be T1 over 2 T1, which is basically then just going to give me a ratio of 1/2. Now, as I'm doing this, this makes sense in my own mind to just go ahead and flip them. So I'm going to go ahead and put invert because period equals 1 over frequency. And then hopefully that should suffice. The next portion says the dashed line in figure 4 shows the kinetic energy versus potential energy of the block cart spring system after the block is dropped onto the cart. This graph is identical to the graph shown in figure 2 for the cart spring system before the block is dropped onto the cart. Briefly explain why the two graphs must be the same using physics principles. So if I'm thinking about this scenario, I'm thinking about the elastic potential energy formula that is 1/2 kx squared, and there is no mass in that setup. Therefore, when it gets stretched out to its maximum stretch, which is the x value, there is going to be no change in the amount of energy that the system initially has, and the k is going to be the same because it's the same exact spring. So let's go ahead and write that idea out. All right, so I put the elastic potential of the system is still the same because 1/2 kx squared doesn't involve mass. That's probably not the best worded answer, but I think it gets the point across. Now, after the block is dropped onto the cart, consider a system that consists only of the cart and spring. So let me try to picture this. So we have a spring, and then we have the cart, and it's just this system, and then not the 3M that's dropped on top of it. Okay, so even though a drawing is potentially very basic or simple, the more visuals you have, the more chances you are that you'll get cued into some correct ideas. So let's go back and read this again. After the block is dropped onto the cart, consider a system that consists only of the cart and the spring. On figure 4, sketch a solid line that shows the kinetic energy of the system that consists of the cart and the spring, but not the block after the block is dropped onto the cart. So if this is the kinetic energy after it was dropped on, it was normally 4m in total, but we are excluding this 3m. So if we just have a single m instead of 4m, that means we're just going to be right at 1 joule because it's 1/2 mv squared, where the mass is directly proportional to the kinetic energy. So now if we have 1/4 of the mass that we're considering and leaving out the rest of it, then we have to have only 1 joule of kinetic energy, and then it's going to slide down over to 4 joules of elastic potential energy, because remember, that is not mass dependent, so it should still hit that 4. For problem number 2, we have an experimental design question with a suggested time of 25 minutes. It says students conduct an experiment to determine the acceleration A of a cart. The cart is released from rest. Put V equals 0 up here. And then at the top of the ramp at t equals 0 and moves down the ramp. The x-axis is defined to be parallel to the ramp with its origin at the top as shown in the figure. The students collect the data shown in the following table. So we have some positions and times, and here it says indicate which quantities could be graphed to yield a straight line whose slope could be used to determine the acceleration A of the cart. You may use the remaining columns in the table as needed to record any quantities, including units that are not already in the table. Now, if I'm thinking about finding the acceleration using some different quantities, What I would do is I would immediately think of doing velocity versus time. So if you're familiar with your kinematic curves, you should be pretty familiar that the position versus time graph slope is going to give you the velocity, and the slope of the velocity versus time graph is going to give you the acceleration. So the thing about it that is a little bit tricky is that as this card is going down, it's going a different speed every second of the way. So the way I'm going to utilize these positions and times is going to be a multi-step process for sure. So if I just take these positions and divide it by these times, it's not going to be an accurate representation of what the velocity is. So what I'm going to do is I'm going to find a delta x between these two and divide it by the delta t between those two. Now, if I just do position or a delta x over t, that's a constant velocity formula. So what I'm actually doing is finding the average velocity of that particular um, time slot from 0.39 to 0.59. So if it's the average velocity, it will reach that average velocity at the midpoint between these two times. So what I'm going to do is I'm going to write down some times that represent the midpoint between each of the two different time slots, and then I'm going to do delta x over t and then write down those average on the side right over here. All right, so I got all my values. I took my delta x divided by my delta t to get the 0.4, the delta x between these two divided by the delta t of these two to get this 0.56, and then so on. For my times, as I said, I took the two times that are adjacent to each other and then just found the midpoint between the two. So from 0.39 to 0.59, it's going to be 0.49 right in the middle, 0.59 to 0.77, 0.68 is in the middle, and then so on. And some of these values are going to be rounded. I put everything to the hundredths place because that's what they provided in their position and time columns originally. All right, so I have some velocities and times that are good representations of what's going on with the cart as it's accelerating down the ramp. So I'm for sure going to want to have velocity as my dependent variable on the vertical axis, and then I'm going to make sure I want to have time on my horizontal axis. The next part says, in the following grid, plot the appropriate quantities to create a graph that we can use to determine the acceleration of the cart as it rolls down the ramp. Clearly scale and label all axes, including units, as appropriate. Draw a straight line that represents the data. So what I always recommend is that you label everything first, because you're not going to forget to plot the points on the actual graph, but you might forget to label everything on the graph. So I'm going to go ahead and label my axes and then put my title on there. All right, so I'm going to take a look at what I have here. I have 4 little boxes leading up to this big solid box, and then I have 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 4 is 32 little boxes. Now, 32 boxes seems a little bit too small to chop up all my numbers. So what I'm going to do is I'm just going to pay attention to these bolded lines. I'm going to use all 8 of those, and then I have 1, 2, 3, 4, 5, 6 on the way up. All right, so let's go ahead and take a look at our data that we previously set up. All right, I have numbers that go from about 0 to 0.75 over here, and that go from about 0 to, we'll say, 1.1 over here. So I just want to make sure that I come up with intervals so that those numbers fall in nicely on my graph. All right, so as I said, my times go up to about 1.1, and this is just a side note. This stuff I probably wouldn't be writing on the actual test. And then for the velocities, they go up to about 0.75. So if I take 1.1 and divide it by 8, because I'm going to have 8 solid lines on here, then I get 0.1375, and then I'll just round that up to 0.15. Now for my vertical axis, I have 6 solid lines going up. So if I take 0.75 and divide it by 6, I get 0.125. Again, I don't think I have to be that particular about the number. So I'll take 0.125 and round it up to 0.15. All right, from there, that looks like a nice interval for me to go ahead and plot my points. So let me go ahead and take a moment to plot these points and do my best drawing a best fit line from there. All right, so I did my best plotting the points. They're not super exact, but I tried my best to place them the best I could. I made a best fit line. Remember, the best fit line doesn't necessarily touch all your points, but you're going to place it in an area that is about where all the points are lying so that you have a good line that represents the pattern of the dots rising on the graph. Now what I'm going to do is go ahead and grab a point here. It looks like it's about at 1.05 and then maybe up to about 0.82. And then down here, it looks like I'm at about 0.15, and then it goes up to about 0.10. So now what I'm going to do is, using the line you drew in part 2, calculate an experimental value for the acceleration of the cart as it rolls down the ramp. So I'm going to go ahead and find the slope, which is 0.82 minus 0.15 over 1.05 minus 0.15. And then I get 0.8 meters per second squared. Now, the accepted value from the scoring guide was 0.75 meters per second squared, but it turns out that you don't have to get that exact slope anyways. All you have to do is attempt to find the slope of your best fit line, and if you do a reasonable job doing that, then you earn your point. So when you're doing a graph, you do want to make sure you're being fairly precise and do a good job finding good intervals for the X and Y axes. So one thing they do grade you on is they want the graph to cover at least half of the blank space given. So that's actually one of the criteria. Let me check the exact wording here. The wording says the axes have a linear scale and are identified so that when graphed correctly, the data will span more than half of the horizontal and vertical axes. So that means that you paid some attention to making some nice intervals on the X and Y axis. So if it was too crunched or didn't fit on the graph, then you would actually lose a point. All right, so moving on to the next part, we have the students are asked to determine experimental value for the acceleration due to gravity using their data, and then what additional quantities do the students need to measure in order to calculate g from A and write an expression for the value of g in terms of A. Now, to me, it seems a little bit more intuitive for me to solve part 2 first, so I'm just going to go ahead and do that. So in order for g to pop up in my setup, I would be taking a look at that cart on the ramp. And obviously, if you have a G value there, you're going to have it pop up in some of your force vectors. So I'm going to have a few different force vectors. Here's my mg. And then we have our horizontal and vertical components. So since this one is opposite of my theta, we have mg sine of theta here. And then we have mg cosine of theta for the perpendicular component. Now, I know from experience that if there is no friction, then this force, which is parallel to the ramp, is going to be my net force, and my net force equals m times a. So with that being said, my masses actually drop out, and then if I want an experimental value of g, then I'm going to divide both sides by the sine of theta. So g equals a over the sine of theta. So I got my experimental A, and then I would have to divide it by the sine of theta, which actually worked out nicely because one says, what additional quantities would the student need? Then I would say theta, the angle of the incline. All right, now part B is complete, so let's go ahead and move on to section C. Part C says the students calculate the value of G, the experimental G, to be significantly lower than the accepted value of 9.8 meters per second squared. What is the physical reason, other than friction or air resistance, that could lead to a significant difference in the experimentally determined value of G? Now, the first things I would think of would be air resistance and friction, but we're talking about a cart rolling, so one of the first things I would think of is the rotational inertia of the wheels. And the second thing I would think of is I would think about it in terms of energy. If it didn't lose energy through heat, then it would maybe be creating some sound energy. So the rotational inertia of the wheels and sound energy. Briefly explain how the physical reason you identified in part C would lead to a decrease in experimentally determined value of g. So the g value is responsible for the acceleration and the velocity of it. So basically anything that sort of slows it down. So I would just say that that rotational inertia takes up some of the total energy value, and then same thing with the sound, and then therefore leaves less kinetic energy for the card itself. So let me go ahead and put that into words. So I went ahead and wrote the translational kinetic energy decreases due to the rotational kinetic energy of the wheels and the sound energy lost to the environment. And then for my final part, it says the student wants to confirm that the acceleration is the same whether the cart rolls up or down the ramp. The students start the cart at the bottom of the ramp and give it a quick push so that it rolls up the ramp and momentarily goes to rest. So it goes up this way and momentarily comes to rest at the top. So go ahead and write as much as possible to cue me in to what's going on. And the x-axis is still defined to be parallel to the ramp with the origin at the top. So of the following graph, sketch the position and velocity as functions of time that correspond to the scenario while the cart moves up the ramp. Okay, so we're only looking at the part that moves up the ramp because I was thinking it was going to move up and then back down. All right, so if it's moving up the ramp, position-wise, it must be moving towards zero. So it's going in the negative direction, and they said this one is positive x. So I'm going to be moving down on my ramp. And then also, if it's going up the ramp, it's going to be slowing down. So I want to have my line come down on the ramp, or excuse me, come down on my graph and become increasingly more flat to show that the rate of that which it's moving decreases. Now for my velocity versus time graph, again, I'm moving in the negative direction. So this portion is my negative portion. So I want to make sure I operate underneath the zero, and I'm going in the negative direction and slowing down. So which means I want to stay under the x-axis and I want to be moving towards zero. So I want a number that starts as a large negative number and then decreases its negative value until it reaches zero. Remember, negative just means it's going in the other direction. It doesn't mean that it's necessarily going slower or faster. So -5 would be faster than like a -3 or a -2. So anyways, if you have anything that's slowing down, you want to make sure it's heading towards zero. So that concludes our last portion of question number 2. Let's go ahead and move on to our next question. For question 3, it's a qualitative quantitative translation problem, which is a 12-point question and a suggested time of 25 minutes. So it seems fairly generous, but I want to make sure that I'm efficient with my time as well. So we have a small block of mass m0 is attached to the end of a spring of constant k0 that is attached to a rod on a horizontal table. The rod is attached to a motor so that the rod can rotate at various speeds about its axis. When the rod is not rotating, the block is at rest and the spring is at its unstretched length L. As shown, all frictional forces are negligible. So for part A, it says at time t equals t1, the rod is spinning such that the block moves in a circular path with a constant tangential speed v1, and the spring is stretched at a distance d1 from the spring's unstretched length as shown in figure 1. At time t equals t2, the rod is spinning such that the block moves in a circular path with a constant tangential speed v2, and the spring is stretched a distance d2, and the spring's unstretched length where d2 is greater than d1 as shown in figure 2. So basically what I'm seeing here is that this one in figure 2, it's got a little bit more stretch. So in my mind, it's got a little bit more velocity and force and stretch, a little bit of all the above. So that's just kind of in the front of my mind. So let's go ahead and check out what the first question is asking. It says, of the following dots, which represents the block at the locations shown in figure 1 and figure 2, draw the force that is exerted on the block by the springs at time t equals t1 and t equals t2, the spring force must be represented by a distinct arrow starting on and pointing away from the dot. Draw the relative lengths of the vectors to reflect the relative magnitude of the forces exerted by the spring at both times. Now, because the spring is exerting a centripetal force or a restorative force, it's pulling the block back in, or attempting to at least. So based on our drawings, it would look something like this. So I want to make sure I have some forces that are pointing to the right, except this one is going to be a little bit larger. So I want to make sure I have a vector pointing to the right this way, and I want to make sure that this one is clearly larger. And referencing D1 and D2, describe your reasoning for drawing the arrows the length that you did in part A1. So for part 2, I'm going to go ahead and put my answer on the side over here. I'm thinking of Hooke's law, which is F equals negative kx, and the spring force is going to be dependent on two things, which is the k value of the spring, which is going to be the same in both cases, and then the x value, the amount of stretch or compression from the equilibrium position. So I know intuitively that that force should have been more, but I want to break that down. So remember, you want to use your equations often to take a look at those relationships and make those connections. So I went ahead and wrote at t equals t2, the x value is greater, therefore the spring force must be greater. And then I have Hooke's law written here, so it should be pretty clear that I was focusing on that idea. Is the tangential speed of the block at t equals t1 greater than, less than, or equal to the tangential speed of the block at time t equals t2? Okay, so the first thing I'm thinking of is that the second one is definitely going faster. So v2 is greater than v1. Justify your answer without equations. Okay, now that's a little bit harder. So I have to kind of link the ideas that I'm thinking about. So I covered that the spring force is greater. That's the centripetal force, which is the net force. So I'm kind of thinking if there's more force, there's more acceleration, which means more tangential speed. So let me go ahead and articulate that in some words and make sure I'm not using any equations while describing that idea. All right, so I think I was pretty clear about that part. I mentioned this force from the spring is larger, therefore the net force is larger, leading to a greater acceleration and tangential speed. So I think that's pretty clear, all the connections, and I didn't use any equations. So let's move on to the next part. B says, consider a scenario where the block travels in a circular path where the spring is stretched at distance d from its unstretched length L. Determine expression for the magnitude of the F naught, or net force, exerted on the block. Express your answers in terms of M naught, K naught, L, and D, and fundamental constants as appropriate. So I already kind of thought through this before, that the net force is the spring force, which is equal to negative kx. So it says express your answer in terms of M naught, K naught, L, and D. So let's go ahead and change that up a bit.
It's Friday, right? It's Friday. See you later.
All right, so it feels like I need to use more because there's an extra term here, but I think that's pretty much it, because the net force is the spring force. So I just used the K that they gave me. They said K naught, and then the D was the amount of stretch. So I replaced my X with the D so that I went by the same terms that they gave me. All right, so that should be it. So I'm going to go ahead and box that up just in case. And then it says derive an equation for the tangential speed v of the block. Express your answers in terms of m naught, k naught, l, d, and fundamental constants as appropriate. All right, so now when we're thinking of tangential speed, I'm thinking of circular motion and centripetal acceleration. So we have this k naught times d, and that should equal mv squared over r. So mass times v squared over r, which is centripetal acceleration. Now, again, I want to make sure that I use the terms that they gave me. So let's go ahead and change the look of this and then solve for a tangential speed. All right, so I didn't necessarily use this anymore. It wouldn't matter if I X'd it out or not. I'm just going to X it out so it's a little bit more clear for your viewing. But this K naught D is the net force. I'd include the negative there to show that it's restorative, but it's the center seeking force that is my mv squared over r. Now it gave me m naught, so I changed my m to just m naught. V squared is just v squared because I want to solve for v anyways. And then I was thinking about my radius, so basically the radius of my circular path, and that is the entire length of the spring, which includes L, the unstretched length of the spring, and then D, the amount of extra stretch it has as it's moving. So I did L plus D for the radius. So I basically did a little bit of cross multiplying, which is taking the L plus D and then crossing it up and over here, and then taking the M naught and then dropping it underneath, and then square rooting both sides. So I got V equals a square root of all of these put together. Now for part C, it says, does your equation for tangential speed V of the block from part B2 agree with your reasoning from part A? So A, I said that the time at T2 where the spring was stretched more would have more velocity. That should still hold up. Wouldn't change now that I'm a different part of the problem, but it says explain your reasoning. And if I'm taking a look at my equation that I just created over here, the mass is the same, the L is the same, but my distance D, the amount of stretch, is the factor that's going to be different. So if I have two larger numbers in the denominator, or excuse me, the numerator, then the entire number as a whole would have to be greater. So let me go ahead and put that into words. All right, so I tried to word that and then make sure I put some good details in there. So the spring is stretched more at t equals t2. So for the second picture, where that d2 is greater than the d1, then it would make the numerator increase, leading to a larger velocity, and then maybe even point a little arrow up there, although I'm sure that they knew that I was relating it to that. So that's pretty much it. The problem didn't feel like it took me 25 minutes at all. I'm not sure exactly how long it took me, but if I maybe took, we'll say, 15 minutes to solve this problem, I might take a peek at the clock and then notice that I have some extra time, and then maybe take another minute or two to kind of scan through my answers, but I don't really necessarily need to use the full time. So I'm going to go ahead and scan, double check this section, and then save those extra minutes so that I could go back and work on problems that are a little bit harder as I move deeper into the free response section. So I hope all those strategies, narrations, and samples were helpful to you in learning how to maximize your potential for the free response section of the AP Physics 1 exam. Remember, check out the document in the description with some more resources, or check out the beginning of the video if you want to write down some of those strategies and implement them on your own. But I hope that was helpful to you. Thank you for watching and listening.